I am so sorry I'm not here to teach you this in person. However, hopefully this video will help and you can always revisit it if you don't understand it the first time. I will be back in a couple days and then you can ask me more questions in class 2 on anything you don't understand. So one of the second to last topics we have to talk about is hybridization. And I don't tell you guys this very often, but it's really not important to get caught up in what it is. You just need to really know how to do it. It's related to the idea of resonance, that when a molecule exhibits, a double bond here and a single bond here, they kind of mix or hybridize to make a new length of bond. And the idea is that the orbitals are hybridizing as well. And that means like an S, which is like a sphere, is combining with like a P that's a dumbbell, and they make a new type of shape. This topic is really dense, so we're going to glaze over it because really AP doesn't go in depth on it. You just have to know how to do it, not what it means. And so when orbitals hybridize, this is the maximum they can be. They can be S with a power of 1. Notice that's an understood 1. P3, D5, F7. And essentially what you're going to do is when a problem asks you to find hybridization, you're going to count the number of areas of electrons. And notice I said areas of electrons. I didn't say count the number of electrons. I said count the number of areas you find electrons. And remember, you find electrons in lone pairs, and you also find them in bonds. So we're counting the number of areas. And once you know the number of areas, say it's 2, okay, you are going to make the powers of that formula in the center total up to 2. So if I have 2 areas, 2 areas, wake up computer, and I want it to total to 2, S is always going to be where you start, and it has a power of 1. S is a power of 1. And then I need one more to total to 2, so I move on to P and I make it a 1. We just don't write 1s, we write SP. If I want it to be 3 areas, I again start at S, but I now need 2 P's to total to 3, because S is 1 and P is 2, and that makes 3. So if I want 4 areas, I'm going to do S, P, what? If you said 3, you are right. So you're already starting to get it. If you want to do 5 areas, S, P, 3 is the max it can take, so you don't do 4, and then you move on to D and do 1 more, SP3D. Now, where do those numbers come from? They're not random. How many orbitals or boxes do you draw for an S? 1. How many boxes or orbitals do you draw for P? 3. D, 5, F, 7. So they're not random. They actually have meaning, which means it should be easier for you to memorize. So how do you actually do this? To actually do it, you are first going to need to draw a molecule. I know it's shocking. So the first thing I'm going to ask you to do is draw ammonia. Remember, ammonia is NH3, not NH4, not NH4 plus, NH3. So on the side of your paper, take a moment to draw NH3 and feel free to pause the video at this time. So now you should have a structure that looks something like this. Sorry, it's not my normal neat, but you get the idea. And what you're going to do is, if you read the question, it wants you to find the hybridization on multiple things, on the N and on each of the H's. So you have more than one answer here. Let's look at the N first. So where do you see electrons? I'll demonstrate. Well, I see electrons here. And I like to think of them as almost clouds. Like I see a cloud of electrons there, an area. I see one here. I see one here. And I see one here. So around the N, there's 4 areas. And I have to make the powers of that total to 4. So S is 1, and I need 3 P's to total to 4. Done. It's really that easy. I know, it's shocking. Chem, easy, right? So now, if you have to do the H's, and pick any H because they're all the same, the bottom H, for example, has 1 area. So what would it be? S. And I'm done. So there's 2 molecules on here. I'm going to ask that you draw both of them, and that you do the hybridization on all the atoms in each picture. And when you guys are ready and you think you know the hybridizations, ask the sub to unpause the video when everyone's done, not just the fastest, and then look and see if you guys are right. So in the case of XeF2, and you do have to put in the lone pairs, because if you don't, you're not going to get the number of areas right. You end up getting +2, which means you should have 6 electrons on the Xe, not 4. When you're doing the hybridization of the xenon, you have 1, 2, 3, 4, 5 areas. So the xenon is going to be sp3d. And the fluorines, both of them are going to be the same. And the fluorine has 1, 2, 3, 4 areas, so it'll be sp3. Same for that fluorine. Now, the other one that I asked you to draw, you should have had something that looks like this. And do you have brackets? Because if you don't, you need to add them into your picture. Okay, now, sorry it's not the neatest, brackets, charge, and then you start counting areas. So in the case of the B, I have 1, 2, 3, 4 areas. So the B is going to be sp3, totaling to 4. Now in the fluorine's case, I have 1, 2, 3, 4 areas, so it is also sp3. In fact, all of the F's are sp3. So now we finished hybridization. Just don't make it harder than what it is. So the next topic is also not difficult in the sense of what I'm asking you to do. I'm asking you to count the number of sigma and pi bonds, and the sign for sigma is right there below, and we generally draw it as a circle with like a horizontal line to the right. It is not this, that's theta. Okay, so you want to draw sigma, not theta. So when you're counting the number of sigma and pi bonds, everything, a single, a double, and a triple, all count as one sigma bond. But any extra lines in the bond, so any extra in the double or the triple, count as pi. So it's pretty simple. Like in that previous molecule we just drew, BF4 minus, there's 4 single bonds. So there's 4 sigma bonds. Now, the problem is that this concept isn't hard, but the molecules they can sometimes ask you to do it with are considerably harder. In fact, this is a picture of an organic molecule. And the first thing you really need to figure out is, what the heck am I looking at? Like, what is that molecule? So I'm going to teach you a little bit of organic chemistry. The first thing that you need to know is that organic is the study of carbon, right? It's carbon-based molecules. And what chemists do is they kind of simplify their pictures by taking out things because they're implied. So for example, the first thing organic chemists do, and you have to know how to fill in these diagrams, okay? So don't just tune me out, is you have to fill in a carbon everywhere there's a vertice or a point on a line. So for example, right there, that's a carbon because there's a point and you need to fill it in. Right here, there's a carbon. Right here, there's a carbon. Right here, there's a carbon. Carbon, 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 carbon. Now, where you see the O and H, there's not a carbon, which is why they wrote O and H. Otherwise, you would think there's a carbon there. So then, that's step 1, if you want to write it down, to remember. Step 1 is fill in all the carbons at the vertices. Second step, fill in all the understood H's. And you're right, I just said understood H's. So there are H's in this picture that are not drawn that you have to fill in. The one on the right that's here, that one is not what I'm referring to. What I'm referring to is you pick a carbon, like this one that I just highlighted, and you look at it and you say, hey, how many electrons is it currently bonded to in the picture? So I see a single bond, that's 2, and I see a double bond, which is worth 4. So in other words, I see 6 electrons off that C. Well, the problem is a C would never stop bonding short of 8. So I have to add an H there with a bond. It's an understood H. Now, this only happens with carbons. So I don't go to this O over here and start adding H's. That's not the way it works. If an H was off the O, they would show it. So now you're going to go to the next carbon. And I'm going to go methodically about this. I'm going to go to the left. I'm going to go counterclockwise. So now this carbon, that I'm going to try to highlight for you if I can figure out what the heck I'm doing. This carbon right here that I just highlighted is going to have 2, 4, 6. So there's an H. And the next carbon has 2, the single bond, 4, 6, so there's an H. And the next carbon, 2, 4, 6, it's an H. And the next carbon, 2, 4, 6, it's an H. Now the next carbon, don't just go, oh, everything gets an H. Slow your roll, okay? This next carbon, if you notice, has 2, 4, 6, 8. It already has 8. It doesn't have a hydrogen off of it. But the next carbon, 2 for the single, and then 4 for the double, that's a total of 6. It has a hydrogen. The next carbon has a hydrogen. But the next carbon that's double bonded to the O, no hydrogen, because it already has 8. So if you notice, if you had never drawn in all those hydrogens, you would have missed all those sigma bonds, and you would get it wrong. So you have to complete the picture. And the last thing you need to do, not because it'll affect single or double bonds, is you're going to need to fill in lone pairs. And to fill in lone pairs, you will need to do it on NO or NO or S. So you don't fill in lone pairs on C's or H's. You fill in lone pairs on O, S, and N. Okay, so as I was saying, you have to fill in the lone pairs on N, O, or S. In this case, there's only one O. So if you look at it, the O has a double bond on it, which is worth 4. Clearly, the O is missing 4 more, but we don't add hydrogens. We add 2 pairs. And no, I don't really care where you put the pairs. Now, why are we doing this? Because question A on a free response could ask you how many sigma pi bonds there are, but question B could ask you about the hybridization of that O. And if you don't draw the lone pairs, then you won't know that there are 2 more areas of density. So there is value in completing the picture. So now that you've completed the picture, we now need to label all the sigma bonds. And remember, everything counts as a sigma, so that's a sigma. And be really methodical because it's very easy to miss one. So sigma 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 sigma. So my answer would be 18 sigma. And then for pi, the only ones we didn't label were the double bonds. So if you notice, like over here, I labeled the top line as a sigma, but the bottom line is now a pi. So I have 1 pi, 2 pi, 3 pi, 4, 5 pi. So my answer would be there are 18 sigma bonds and 5 pi bonds. Now, what you may want to do if you're not going to count as you go, like I just did, if you're going to label them all and then go back through, you might want to cross them off as you count. Like I counted that sigma, 2, 3, 4, 5, 6, because you will forget. Trust me, you will forget what you just counted. So there's another one on here. This is actually a molecule in the electron transport chain or system. And we're going to talk about this particular picture. Don't stress about R. I've never seen element R. R in chemistry means anything can be attached there, so it doesn't have to be a particular thing. And remember, for us, it doesn't make any difference because I'm counting bonds, so I don't care what R is. You're not going to fill in lone pairs or H's off R. You're just going to count bonds. However, before we do that, remember, we first need to go back and put in all the what first? Carbons. So this on the left, in this area here, you'll see that the carbons are already written. So don't add one, but go around the rest and at the vertices put all the carbon atoms. Now that you have all the carbons, remember it's time to put in all the H's. And I have to tell you, something we need to discuss are these H's over here. Is it necessary to write them out any differently? Well, my question is if you left it like that, would you catch the fact that this means there are 3 bonds here? Because you have to be able to count those in addition to the other ones you're going to fill in. So my suggestion would be to actually fill in the 3 bonds off of the carbon so that you don't forget to count them. That's what I would do. So now go around, pause the video, put in the rest of the H's and the lone pairs on all the N's and O's that are needing it, and then unpause the video when the majority of the class is ready and see if you are right. So you should have a hydrogen here and a hydrogen there, kind of out of space, but there are no other places needed for hydrogens because all the other carbons have 8. For lone pairs, this N needs two electrons or one pair. The N on the bottom needs 2. The N on the top right needs 2. And the N on the bottomish right needs 2. And then both O's need 2 pairs. So now I challenge you. Pause the video, label the bonds, and count them. And trust me, go slow. Alright, so you should have gotten 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and I know I missed one, 30, right in the middle. So there's 30 sigma, and then if you go back, and this is terrible how small I did this, plus writing on an iPad is not helping, but if you go back and you were to look at the pi bonds, you would have a pi bond here, 1, 2, 3, 4, 5, 6, 7, 7 pi. So if you got 30 sigma and 7 pi, you are right. So now, this is technically the end of chapter 9 and 10, but remember, I asked you to print supplemental notes. Those supplemental notes are about potential energy bonding diagrams, so you need to get those out so that we can discuss them next.